I had the photo-induced electron transfer paper by Voltage et al. I did that because they're French. So photo-induced electron transfer is important in several systems, both natural and synthetic. One of the easiest natural systems to use as an example is photosynthesis, where you have light that comes in as a photo-induced portion and it strikes a chromophore, leading to an excited electron that can go through several redox reactions and eventually lead to high energy molecules like NADPH and ATP to power some of the cell's processes. A synthetic example is solar energy conversion. So here I have a ruthenium-based dye, and that dye would get hit by sunlight, cause a high energy electron, which would eventually travel into the whole conductor and create electricity to power your appliances or your house. So in this paper, the authors made several different DSA complexes. So what exactly is a DSA complex? Well, the D stands for donor, and in this case, they used the osmium-2 bis-terpyridine species as their light-triggered electron donor. S stands for spacer, which was either a biphenyline or a phenylene xylylene spacer, and A stands for acceptor, so it's going to accept that electron from the donor. And they used the N-pyridyl 2,6-diphenyl pyridinium ion. So here's kind of an overview of all the species that they synthesized in the compound. The major differences are between 1 and 2. There's an extra methyl on the terminal pyridine to give it a positive charge. And then between 2 and 3, instead of a biphenyline spacer, there's a phenylene xylylene spacer. After synthesizing these, the next step that the authors took was to investigate the redox behavior. So the oxidation potentials of 1, 2, 3, and D were all relatively the same, whereas the reduction potentials were significantly different, with D being the most negative. And they attributed this to straightforwardly the reduction potential was assigned to the pyridinium species, so it didn't really involve the donor. And then after the redox behavior, they did some absorbance investigations, and they found that the species each produced about 3 of the same absorption peaks. So there's a ligand-centered, a singlet metal ligand charge transfer, and a triplet metal ligand charge transfer. So the singlet metal ligand charge transfer occurred at about 493 nanometers and probably leads to an orange or red color, while the triplet metal ligand charge transfer occurs about 676 nanometers and probably leads to a green color. So remember that these are metal ligand charge transfers because your system has a bunch of pi acceptors, which increases or creates a pi antibonding orbital that's higher in energy that those metal electrons can jump into. So they bounce from the metal to the ligand into those pi antibonding orbitals. So here's an example of the electronic absorption spectra where the red is the donor and the blue is number 2. And what they found was over 430 nanometers, the species exhibited the exact same spectra. And so they compiled this absorption spectra with redox evidence, and they found that the DSA can be considered a supramolecular species, and it has relatively weak coupling between the donor and the acceptor. So from there, they did some computational studies to see which molecular orbitals probably were attributed to or were involved in these absorptions. And they found 3 absorptions peaks. So there's one at 459, and then these 3 from 391 to 399 all created one signal that they referred to as 395 nanometers, and then the third one was at 359. So the first 2 at 459 and 395 nanometers represented a classical metal ligand charge transfer absorption, while the one at 359 represented a charge transfer between the spacer and the acceptor molecule. So here's the results of their computational studies. So here are the molecular orbitals. Down here you have the HOMOs, and up here you have the LUMOs. Where the red arrows are, this indicates that a metal ligand charge transfer was involved. So these orbitals are involved in the metal ligand charge transfer. And the blue is just simply the charge transfer between the spacer and acceptor. So one that I kind of want to key in on is the absorption at 459 involved this H-1 HOMO and then this L+2 LUMO. So this was kind of significant because it ended up creating a D plus S A- species. So this led to the electron transfer. As you can see in the LUMO, you have your acceptor LUMOs that are involved in the transfer of the electrons. So this H-1 L+2 at 459 nanometers kind of corresponds to that D plus S A- system. So if we summarized everything, you have your ground state DSA complex. It gets hit with light and gets excited. So now you have your excited donor system and then your SA. From here, the excited electron gets transferred into a virtual state of the spacer. So you have a D plus S minus system. And this high energy electron is going to relax down into the acceptor molecular orbital and create your final D plus SA minus system. So you've transferred an electron from the osmium 2 and created an osmium 3 complex, and that electron flew or flowed all the way to your acceptor molecule. So thank you for listening.